In this lesson, we are going to learn how to differentiate exponential and logarithmic functions. So far, we covered the power rule, the product rule, the quotient rule, and the chain rule. Those are the tools. Today, we are adding two new families of functions to our toolkit, exponentials and logs. Here's what we'll cover. In the first half, we will start with the derivative of e to the x, then extend it to any base, a to the x. I will show you exactly where the natural log comes from, so we'll never have to memorize it blindly. In the second half, we'll move to the logarithms, starting with natural log x, then log base a of x. Same idea, I will show you the formula, prove why it works, and then we'll practice with 20 examples, from the basic to exam level. By the end of this lesson, you'll be able to differentiate any exponential or logarithmic functions confidently. Let's get started. Let's start with the derivative of exponential functions. The formula for the differentiating e to the something is simple. E to the box differentiated gives you e to the box times box prime, the derivative of whatever is inside the box. That's it. Keep the exponential as it is and multiply by the derivative of the exponent. Let's test this with the simplest case, y equals e to the x. Here the box is just x. So we get e to the x times the derivative of x, which is 1. So dy by dx is e to the power of x times 1. That is e to the x. The function equals its own derivative. That's what makes e so special. Now on the right, what if the base is not e? What if we have a to the box instead? The formula is almost the same, a to the box times box prime, but now we have one extra factor, ln a. Let's test it. Y equals a to the x, the box is x, so the box prime is 1. dy by dx equals a to the x times 1 times ln a. But where does this natural log a come from? Let me show you why. Actually, let me first rewrite the formula on the left. The derivative of the e to the power of x is really e to the power of x times x prime times natural log e. Natural log e equals 1, so it disappears. That's why we don't usually write it. So the natural log is always there. It's just hidden when the base is e. Now let's prove the formula for a to the x. The key idea is to convert a into e form. If you let ln a equals b, that means log base e of a equals b, which means a equals e to the b, which is e to the ln a. So we can rewrite y equals a to the x as e to the ln a raised to the power of x, which equals e to the ln a times x. Now this is just e to the something, so we know how to differentiate it. So dy by dx equals e to the ln a times x multiplied by the derivative of ln a times x, which is just ln a. And since e to the ln a times x is the same as a to the x, we get dy by dx equals a to the x times ln a. And that's where the natural log a comes from. It's not something we memorize out of nowhere. It appears naturally when you convert any exponential to base e. Square root of e to the negative 3x squared plus 5. This one looks intimidating, but the box method makes it manageable. Let's start with the outer box, the square root. Using the square root box method, the box prime over 2 root box, the box is e to the negative 3x squared plus 5. So we get the derivative of e to the negative 3x squared plus 5 over 2 root e to the negative 3x squared plus 5. Now we need box prime, the derivative of e to the negative 3x squared plus 5. The 5 is a constant, so that disappears. So we just need the derivative of e to the negative 3x squared. Using the exponential box method, e to the box times box prime, the box is negative 3 squared. So the derivative of e to the negative 3x squared is e to the negative 3x squared times negative 6x, which is negative 6x e to the negative 3x squared. Now let's put everything together. dy by dx equals negative 6x e to the negative 3x squared over 2 root e to the negative 3x squared plus 5. The final answer is negative 3x e to the negative 3x squared over root e to the negative 3x squared plus 5. Two boxes, the square root box on the outside, the exponential box on the inside. Peel off one layer at a time, and even a problem like this becomes routine. All the examples so far has been base e. Now let's see what happens when the base is something else. And this is where that ln a factor we proved earlier becomes essential. Y equals 7 to the negative x plus 10 to the x squared. This is where the a to the box formula comes in. A to the box differentiated gives a to the box times box prime times ln a. Let's take each term separately. First, 7 to the negative x. A is 7, the box is negative x. Box prime is negative 1, so we get 7 to the negative x times negative 1 times ln 7. Next, 10 to the x squared. A is 10, the box is x squared. Box prime is 2x, so we get 10 to the x squared times 2x times ln 10. Putting both terms together, dy over dx equals negative 7 to the negative x times ln 7 plus 2 times 10 to the x squared times x times ln 10. Same box method, just one extra piece, natural log a. When the base is e, natural log e is 1, so it disappears. When the base is anything else, then natural log ln stays. That's the only difference. Let's push it further, quotient rule with a non-e base, the inverse of exponentials. You will see the same natural log pattern appear, just in a different position. Here are the two box formulas for logs. On the left, natural log of a box differentiated gives the box prime over box. The derivative of the box on top, the box itself on the bottom. On the right, the derivative of the log base of a of a box gives the box prime over box times ln a. Same structure, just with the natural log a in the denominator. The box is x, the box prime is 1, so dy over dx equals 1 over x. Simple. Now let's test the right one, y equals log base 10 of x. The box is x, the box prime is 1, and a is 10, so dy over dx equals 1 over x times ln 10. But where does this ln 10 come from? Let me prove it. We can rewrite log base 10 of x using the change of the base formula, ln x over ln 10. That's the same as 1 over ln 10 times ln x. Now, 1 over ln 10 is just a constant, so when you differentiate, dy over dx equals 1 over ln 10 times 1 over x, which gives us 1 over x ln 10. Same answer. The formula works because it's just a change of the base rule built into the derivative. Now, here's the key insight. Look at the left formula again. I'm gonna add something in. The derivative of the ln of box is really box prime over box times ln e. It was always there, but ln e equals 1, so it's been hiding. Now, compare the two formulas side by side. On the left, box prime over box times ln e. On the right, box prime over box times ln a. They are the same formula. The only difference is what comes after the box in the denominator, natural log of the base. For natural log, the base is e, so you get ln e, which is 1. For log base 10, you get ln 10. For log base 2, you get ln 2. For log base a, you will get ln a. So you don't need to memorize two separate formulas. It's one formula, box prime over box times ln of the base. And when the base is e, the ln disappears. Exactly the same pattern we saw with exponentials. Now let's practice. We'll start simple and build up just like we did with the exponentials. Now pay close attention to these three examples. They look similar, but they are very different. Number 1, y equals ln x to the 4. Before we even touch the box method, let's simplify first. Using log rules, ln x to the 4 equals 4 ln x. Now, this is just constant times ln x. So dy over dx equals 4 times 1 over x, which is 4 over x. Number 2, y equals ln x all to the power of 4. This is completely different from number 1. Here, ln x itself is being raised to the 4th power. So we use the power rule box method. Box to the n gives the n times box to the n minus 1 times box prime. The box is ln x. Box prime, the derivative of ln x, is 1 over x. So dy over dx equals 4 times ln x cubed times ln x prime, which is 4 ln x cubed times 1 over x. So the final answer is 4 times ln x cubed over x. Make sure you see the difference. Number 1, the power is on x inside the log. Number 2, the power is on the whole ln x. Completely different answers. This is one of the most common mistakes on the exam. Number 3. Y equals the square root of ln x. Using the square root box method, the box prime over 2 root box. The box is ln x, box prime is 1 over x. So dy over dx equals ln x prime over 2 root ln x, which is 1 over x over 2 root ln x. To clean this up, we multiply top and the bottom by x. The final answer is 1 over 2x root ln x. These 3 examples show why notation matters. ln x to the 4, ln x all to the 4, root of ln x. 3 different functions, 3 different derivatives. Identify the box, find the box prime, plug it in. The key is knowing which box method to use. Y equals natural log of x plus 1 over x minus 1. Now your first instinct might be to use the ln box method directly, box prime over box. But look at what the box would be. It's a fraction, x plus 1 over x minus 1. To find the box prime, you need a quotient rule inside the ln formula. That gets messy fast. Let's not do that. There's a much better way. Use log rules first. Simplify before you differentiate. ln of fraction equals ln of top minus ln of bottom. So y equals ln of x plus 1 minus ln of x minus 1. Now each term is a simple ln box. First term, the box is x plus 1, the box prime is 1, so we get 1 over x plus 1. Second term, the box is x minus 1, the box prime is 1, so we get 1 over x minus 1. dy over dx equals 1 over x plus 1 minus 1 over x minus 1. Clean, simple, no quotient rule needed. Let's apply the same idea to a harder one. Don't even think about using the box method directly on this. Let's expand using log rules first. ln of the top minus ln of the bottom. That gives us ln of x to the 5th minus ln of x plus 1 times x minus 1. Now ln x to the 5th equals 5 ln x, and ln of x plus 1 times x minus 1 equals ln of x plus 1 plus ln of x minus 1. 3 simple ln terms, each one is a basic ln box. dy over dx equals 5 over x minus 1 over x plus 1 plus 1 over x minus 1. That is 5 over x minus 1 over x plus 1 minus 1 over x minus 1. Imagine trying to do this with a quotient rule inside the ln box. It would be a nightmare. But with the log rules, 3 simple boxes, done. This is a really important lesson. Whenever you see a ln of product, fraction, or power, expand it using log rules first. Then use the box method on each simple term. Simplify first, differentiate second. Your future self will thank you. First, natural log is always there. For base e, it's hidden because ln e is 1. For any other base, it appears as a multiplier in exponentials and a divisor in logs. Second, simplify before you differentiate. Log rules can turn a complicated function into simple terms. Always check if you can expand first. Third, no matter how complex the problem looks, it's always just boxes inside the boxes. Find the outer box, find its derivative, work your way in, one layer at a time. Well then, see you in the next topic. This has been Alex.